Hello, I welcome you all. The problem read, draw the shear and moment diagrams for the beam. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. Right, so let's draw a free body diagram. We have a tension force there that I'm going to call C. Okay, and then I have a vertical reaction at the hinge A and horizontal reaction AX, and then I have an equivalent force here, which is the area under the loading diagram, which is just 250 by the length of the loading distributed load, which is 2 times 250 by 2, which gives us a 500 newtons, right? And it is acting at the location half of 2, which is a meter from A. Okay, great. So let's find the support reactions quickly. We have summation, of moments, about point A equal to 0, and clockwise being our reference, and clockwise being our reference positive. We have a minus 500 by 1, and then we have minus 500 by 2, and then we have we are going to have components here. We have components. The slope for this, let's just indicate the slope for this. This is a 4, this is a 3, so 3 squared plus 4 squared. 3 squared is 9 plus 4 squared, 16 plus 9, that's 25. Root of 25 is 5, so this is 5. Yeah, so then we are going to have components. We'll have one component like so here, and this one is going to be equal to C times the rise divided by 5, and then we have C times the run divided by 5. Alright, so we continue. Then we are going to have a plus C by 3 over 5 times 4. Then this equal to 0. Therefore, our C will give us minus 500 by 1, of course, minus 500 by 2, okay, and then divided by 12 divided by 5, right? Okay, so what do we have? We have a 625 newtons. Let me just repeat this. Okay, $625, right? So summation of forces in the y equal to 0. Okay, this is summation. We have AY, we have minus 500, and the plus a C3 over 5 equal to 0. Therefore, our AY is just going to be equal to 625 times 3 divided by 5. Okay, and then minus 500 minus 500. So AY is going to be equal to 625 also. Is that so? Okay, is that so? Let me see again. Okay, 625 plus 500. It's 1,000. So 625 plus 625 by 3 divided by 5. It's 1,000. Okay. Then we have summation of forces in the x direction equal to 0. What do we have in that direction? We have ax minus c times 4 over 5 equal to 0. Therefore, ax is going to be equal to c is 625 times 4 divided by 5. So ax gives us a 500. So this is a 500. Okay. Alright, so this is a 500. So we have all the values. Let me just update them. We have all the values. Ax is equal to 500. Ay is equal to 625. And the cy is equal to just c, not cy. C is equal to 625, right? Okay. Yeah, I think that's about it. This is about it. This one here, cy, c3 by 625 by 3 divided by 5. This is a 375. And then this one is a 500, right? Yes, that's a 500, right? Okay, so with this information, we can now go directly and start doing the plots. Let's do the plot quickly. Let's put the loading there like so, up to somewhere there. Let's put the line for shear, and then let's put the line for the moment. So we have A, B, somewhere there, C. Okay, we have the distributed load like so, up to B, somewhere there. Okay, this is 250 newtons per meter, right? And then we have 625. Then we have a 500. Okay, then we have a loading here at B, which is a 500 also. Then we have also two loadings there from the cable. Okay, one is 375, and then the other one, this one is 500, right? And then the dimensions, let me get rid of that. We have, this is from there to there. So this is 2 meters. This is 2 meters. Okay. So plus and minus. We have plus and minus. Great. Great. We have found all the support reactions and all the forces in the beam. So what we are now going to do is to draw the shear and the moment diagrams. But we are not going to do the shear, I mean the sectioning, like we've been doing in the previous videos, which we can still do. We're going to draw them directly using these relations. We know that dv dx is equal to negative over the load, all right, because our load is pointing down, and also the derivative of moment dm dx is equal to the shear force. So with these relations, we're going to use them to do our plotting here. Okay, so these relations are quite very vital, and I'll explain as I go on. Okay, so in the first case, of course, this is our shear force diagram, and this is our bending moment diagram. So at A, okay, at A, we have shear over 625. So let me draw it like this, up to somewhere there, okay, maybe up to somewhere there. All right, so this is 625 newtons, right? And then from A to B, okay, we have this distributed force of 250 newtons per meter. From this relationship, this derivative of shear and moment, we know that when loading, like in this case, the loading is constant, but this is negative loading. So let's say loading, okay, is negative, it's negative and it is constant. Okay, we expect the slope for shear to be also negative, and the value of the slope will be constant. So loading negative constant, okay, which is the case here, this is 250 newtons per meter, which is pointing downwards because our convention is like so. Anything up is positive in the y, and that direction is positive in the x. So we are saying loading going down is negative, so it's negative and it has a constant value. All right, okay, it has a constant value throughout, right, which is 250 newtons per meter from A to B. So if this is the case, then therefore we expect the slope to be negative, all right, and it will have a constant value. All right, it will have a constant value. Okay, so when loading has a negative, is negative and it is constant, the slope or the slope of the shear force will be negative. All right, it will have a negative constant value, right? So it will be a linear line with a negative gradient, right? So the slope from 625 newtons is going to be decreasing at the rate of 250 newtons per meter. So what we are going to do now, we are going to do the subtraction. All right, so what does 625 minus 250, okay, we convert it to an equivalent force times 2. What does it give us? All right, let's grab our calculator. 625 minus 250 times 2. So it gives us 125 newtons. Just like we expected at B, okay, we expect a 125. Let's imagine this is a 125. Let me just put a dotted line there. Okay. Okay, so we have 125 there newtons. Okay, and this is uh, the slope. Okay, it's the shear, okay, diagram, or the shear force itself will have a negative, okay, constant slope. Okay, it's negative constant slope. Okay, right. And then the moment we cross at the same point B, we have a concentrated load of 500 newtons. So what this means is this particular shear from 125 will be reduced further by 500 newtons. So we have 125 minus 500. So we see this being reduced further. So 125 minus 500, this gives us a minus 375, right? So let's draw a line. So we expect a further reduction from this point, okay, up to, let's say, somewhere there. Okay, let's say this is our, we say this is our one, this is our one, I mean our 375. This is our 375. Great. So once this happens, let's look at the interval BC. When we look at the interval BC, we do not have any loading, okay, in that space. So what does this mean? Again, using these relationships here, derivative of shear, okay, so we know that when the loading is equal to 0, all right, we expect the slope of the shear, okay, to be equal to 0. Okay, it is as simple as that. When the loading is 0, the slope for the shear is going to be equal to 0. Okay, so this is just going to be a straight line with zero slope. This is 0 slope up to this point. When we reach this point at C, there is a load of 375 which is going up. So it means, so from 375, which is a minus, okay, then plus this loading at C, which is 375, therefore we have a shear of 0. So our shear diagram finally closes at C. And this is what we expect, okay, closes like so. Right, so our shear diagram is this is negative at the bottom, is finally done. This is positive. All right, so our shear diagram is finally done. Okay, so now we are going to move to our moment diagram. We are going to move to our moment diagram, and we are going to use the same relationships. Now here we'll be using the derivative of moment, the dm dx. Okay, right, so let me wrap this. There we go. Okay, so we know that when you look at the shear here, the shear itself, the shear loading, the shear is positive and is reducing, okay, from 625 to 125. So shear is positive, and it is decreasing, okay, right? Therefore the slope for the moment is going to be positive but it will be decreasing. Okay, is that clear? The slope for the moment will be positive but decreasing. All right. So for this to decrease, which curve would you pick? Would you pick this curve for the moment like this? Which one? Whose slope is positive? Okay, this like this or like this? Of course, both of these can be positive, but which of the two has a decreasing slope? The one on top or one or two? Which one has a decreasing slope between one and two? Of course, it is one, right? Okay, it is one. Okay, one has a it is positive. Both of them we are saying they are positive, but the first one is the one that has a decreasing slope, because you see slope is decreasing at every tangent point, right? It is decreasing, while in the case of two the slope is increasing, right? So it's the first one. Great. So if we are to do a plot here, and again, the other thing to take note of is when slope is a polynomial, if when the shear is a function, okay, or a polynomial of degree 1, okay, then it means the moment will be a polynomial, okay, with degree 2. That is how it moves. So it is always one step ahead. So if the loading, okay, is governed by a polynomial of degree 1, it means shear will be degree 2 and slope degree 3 in that order. So the shear force rate this time around is of degree 1. This is a linear function. Then you expect the moment function to be of degree 2. So this is going to be a quadratic function. But it will be positive, okay, in the region A to B, but decreasing slope. Right. So it will be something like this, decreasing, decreasing, decreasing up to that point. Right. That's the point where we have the maximum, right? Okay, we'll calculate this maximum later on. Let's move to the interval BC. The interval BC, what do we have? In the interval BC, we have the following. The shear itself is negative. The shear is negative, right? It's negative, and it has a constant value, right? It's 375, it's negative. Therefore, the slope of our moment, okay, is also going to be negative, and it will have a constant value. All right, see? So that becomes a linear, right? It's a linear function, right? Therefore, from B to C, we just expect a drop, like so. Great. So this is about it. Let's calculate now this value here, okay, where we have the maximum at B. How do we calculate this value? Again, we know from the same derivatives of shear and moment, we know that the area under the shear diagram gives us the moment, right? The area under the shear diagram gives us the moment. So we can either use this portion here, okay, to find this maximum point, which will give us also the same value if you used this one here. It doesn't matter which one you use, right, for this particular case. So let's use we can try both of them. Let's call the first one, let's call the one on the, let's try the one on the left hand side. We say left hand side, we just want to compare them. This is trapezoidal, so we say area is going to be equal to 625 plus 125, right, times half, then times the length, okay, which is, or if you would want to call it the height, which is 2, right? So what does this one give us? Let's grab our calculators. 625 plus 125 times 0.5 times 2. So this gives us 750. So we have 750 Newton meters. Let's try the right hand side. Okay, what we have, area is going to be, because this is just rectangular, 375 times 2. What does this one give us? So 375 times 2 is just 750 or so. So we've seen both cases give us the same result, and this should be like that. And this moment in here is positive, a lot of it. Right, so we are done for this particular problem. We are done, and I hope the video was helpful. If it was, give me a thumbs up, like my video, and continue subscribing to my channel. Bye bye, and see you in my next screencast.